Okay, so now that we know how to make an alkane, what happens if we want to stop at the alkene? So, if you want to stop at alkene, the first thing we're going to talk about is making a cis alkene. And it's all dependent upon my catalyst. So, remember, with your catalyst, a solid catalyst, okay, like palladium, my hydrogen adsorbs onto it. And so this bond's a little weaker, so then my alkyne can come in. And I'll add my hydrogen. And then you do that again. Once I get my alkene. Okay. So how do we stop it from doing it again? How do we stop it so all I get is my cis alkene? And the way we do that is we don't use just pure palladium, because palladium is too reactive and it'll just continue to do the hydrogenation of the alkene. So what we do is we call it poison. We poison the catalyst, and this makes it less reactive. Okay, so our poison catalyst is we use palladium with barium sulfate. Okay, and it's in the presence of quinoline and methanol. This poison catalyst is called Lindlar's catalyst. So you may not necessarily see all of this. If you just see Lindlar's catalyst, you know it's going to be a poisoned palladium catalyst, but this is what's in there. So if we did a reaction with Lindlar's catalyst, let's compare. If I just do hydrogen and palladium, it will go all the way to the alkane. Okay? If I use this is my but2-ine, right? But instead, use Lindlar's catalyst. Remember, we said that was going to be palladium on barium sulfate with quinoline and methanol. If we use Lindlar's catalyst, doesn't matter how much hydrogen gas you have, you only stop at the alkene. It is not strong enough to catalyze it and go further to the alkane. So that's how we make a cis alkene. What happens if you want to make a trans alkene? If you want to make a trans alkene, then you're going to do it this way. To make a trans alkene, you're going to do a reduction. Yes, sodium metal with liquid ammonia, okay, and you get a trans alkyne. Okay, so what is happening here? Okay, so let me just give you the first step of the mechanism before I erase the board. So the first step of the mechanism is this. When you have ammonia and sodium metal, what you get is you get your sodium ion and you have your electron complex with ammonia. And this turns this gorgeous royal blue. So this is going to be at minus 33 degrees Celsius because this is liquid ammonia and solid sodium. Okay. Why aren't we getting sodium ion? Because I don't have my iron 3 catalyst. It's just putting sodium metal and liquid ammonia, and this is what you get. So let's look at the mechanism for this reaction. Okay, so R, C. This is what I have. I have my alkyne, and what I have is my electron that's complex to ammonia. Okay, and my electron will attack one of my carbons, and here 2 electrons get pushed onto that carbon. So what happens is this. You get R, C, C minus, double bond. This is my radical. This is R prime. Okay? And I'm in ammonia. So what now happens is this. These electrons grab this hydrogen. Okay? So what I get, RC, okay, I get this radical plus my ion. Okay, now you can see where this is going. I get an electron, and that goes up my orbital here. Okay, this is a vinyl radical. All right, so just so you know what this is called, vinyl radical. Now, once my electron goes in there, I now form another vinyl radical. And then I have ammonia. Okay. And with that, I get my final product, which is a trans alkyne. Okay, and then again, you get a second amine. Okay, so here's the thing. Why do I get the trans? Well, when it does the attack here, it kicks out that lone pair, those 2 electrons here. So it's going to be on opposite sides of the double bond. Now, why does it stay in the trans configuration? Because there's no rotation around this double bond. So once I form it in the trans, it's going to stay in the trans. So this is the mechanism behind making your trans alkyne. So let's give you some examples now. So your examples are this. Let's take 2-butyne. react it with sodium metal and ammonia. Let's take terminal alkyne. Let's do platinum today. Platinum and hydrogen. Okay, and let's take dicyclohexylacetylene, and let's go ahead to hydrogen and Limber's catalyst. Okay, so what would you get for your products? The first one, you're going to form a trans alkene. This one, nothing's poisoned. You're going to go all the way to your alkane.
How are you going to enforce rules when you don't even follow them?
On this one, with Lindlar's catalyst, you're going to form a cis
What do you mean? I told you I won. Are you brain dead?
a cis alkene.
Follow your own rules. How am I disrespectful?
Okay, now that we've covered the addition of hydrogen gas across my triple bond, hydrogenation, where we saw it as go to all the alkane, completely alkane, or with a poisoned palladium catalyst, Lindlar's catalyst, you form the cis alkene, or with sodium metal and ammonia, you form the trans alkene. Now, if you look at the addition of halogens, if I use only 1 mole of my halogen, and that's going to be just chlorine or bromine, you're going to form a mixture of the cis and the trans alkene. If I use 2 moles of my halogen, then basically you're going to get your tetrahalides as a result. Okay, so depending upon the moles of halogen, you'll either get a mix of cis and trans alkenes, okay, or if I have 2 moles, you'll get a tetrahalide. Okay, what happens if you add a hydrogen here? Okay, and in this case, we're going to give you a terminal alkyne, and the reason is this. You're going to have a similar situation. It'll be a Markovnikov type orientation. The hydrogen adds to the least substituted carbon and my nucleophile to the most substituted. So with 1 mole of HX, we'll get this product. Okay, with 2 moles of HX, the first mole forms this. The second mole, again, hydrogen goes on the carbon with the fewest substitutions, and the halogen goes on the carbon with the most substitutions. So you're going to get a geminal dihalide. So just be aware, this is going to be a Markovnikov orientation. Okay, so when you look at the mechanism going to look very similar to what we've seen before. That is your mechanism. What you're going to form is a vinyl cation. Which is stabilized by your substitution, by the R group. Okay, and that's why you get the Markovnikov orientation. Okay? So, let's go through and do an example. If we take phenyl acetylene and I react it with 2 moles of chlorine, okay, and then let's say we'll take cyclooctane, 1, 2, 3, 4, 5, 6, 7. Let's make it. It's just a little different. Okay, and I reacted with 1 mole of HBr. And let's take pent 1 ine, and I reacted with 2 moles of HI. Okay? So remember, we're adding a halogen across. It can only be chlorine or bromine. If we're adding HX, it's going to be HBr, HCl, or HI. So this one, because I'm adding 2 moles, the first one will add across, form a double bond, but then the second mole will add across, and I get my tetrachloride. Okay, so that's what you're going to get for your product. This one, remember, it's going to be a Markovnikov addition, but it's only 1 mole of HBr, so you're going to get an alkyne. So you're going to get a vinyl bromide. On this one, okay, pent 1 ine, 1, 2, 3, 4, 1, 2, 3, 4, 5. That's my 1. So it's a terminal alkyne, just so you know. Okay, so 2 moles of hydrogen iodine. Remember, hydrogen is going to go to the least substituted carbon right here. So you're going to have this carbon with the iodine, hydrogen, hydrogen, iodine. So 1, 2, 3, 4, 5. So you're going to form basically a 2,2-diiodo pentane. Okay? So those are examples, some of the examples of addition reactions with alkynes. Now let's talk about addition of water to your alkyne. If we look at the addition of water to my alkyne, the general form is going to look like this. We're going to use mercuric mercuric sulfate, okay, with some acid, okay. You may also see it as mercuric sulfate, just with the hydronium ion. And what happens is, you add water across in the Markovnikov fashion. This is called an ene-all, alright? But what happens is it doesn't stay this way. This, what we call tautomerizes. I'll put it on the other side to have more space. What you get is a ketone. And in fact, okay, it's an acetone derivative. Alright? Now, here, if we look at the mechanism, we have Hg2+, okay? And from the Hg2+, what you form is this, a vinyl cation. Okay. From here, you have your water. Attach here. Okay. And finally, let me just rewrite this up here. React it with the water. So we get this. We have more water. That removes this hydrogen. So this so far, this is what we get. Okay? An organomercurial alcohol. And then what happens is, remember I have sulfuric acid present. This attacks there. Alright. And you get Hg plus here. That's a plus charge right there as well. Alright. Remember, this is in resonance form. You say, wait a second. I have a plus charge here and a plus charge there. How does this all work? Don't forget. This is in resonance, right? Now, what happens in this case is that with the alkene, don't forget we used the sodium borohydride and we did a reduction to scramble to remove the mercury. In this case, we regenerate that mercury too. So how do we do that? This lone pair, or not lone pair, these two electrons here move here to form the double bond. Remember I have a plus charge here. When that happens, I get this and I regenerate my Hg2+, my mercury 2 ion. Okay, and this then tautomerizes to become a ketone. So what we're going to do next is we'll go through the mechanism to show how this part tautomerizes. Okay, so we talked about adding water across the triple bond, and we were using mercuric sulfate in the presence of water and sulfuric acid. Okay, and at the end, when you add the water and it adds in a Markovnikov orientation, I added a hydrogen on the least substituted carbon, and I added my hydroxyl group on the most substituted carbon, and I form this product. This is called an enol. So this is my enol. In the presence of acid, okay, we can do what we call an acid catalyzed keto-enol tautomerization. It's not resonance because I'm physically breaking and making bonds. What happens in this case is that in the presence of acid, my double bond attacks the acid, and this is a hydrogen, is bonded to the carbon, and I form the carbocation right here, which has a resonance form. And the resonance form is that these electrons move down and they form the double bond. Okay, so this positive charge is distributed between the carbon and the oxygen. When I look at this form, because I have a delta positive hydrogen, my water, the solvent, will take this hydrogen and the electrons go into the oxygen as a lone pair. And what I get is a keto. This is a keto form because I have a carbonyl here. I get a keto-enol tautomerization. And you can see I regenerate my acid back. So, in summary then, when we look at the addition of water across an alkyne, you don't form, actually, you don't form an alcohol. Mercuric sulfate, you need the Hg2+, and in this case, unlike with our alkene, right, the mercuric acetate, then mercuration, and then the demercuration, in this case, what we get is we get this back. You are going to form a ketone. And your water adds in the Markovnikov orientation. Okay? So then, what happens if you want an anti-Markovnikov orientation? like we did for our alkenes, where we did the hydrogenation, oxidation, you're going to do something similar here. But instead of using diiso, which is the same as saying isolating. So, what you do is you use basically the isoamyl borane as your reagent for alkynes. Okay. And this is similar, okay, but bulkier and less reactive than borane THF that we use for alkenes. Okay? So, one of the keys here is when you look at your alkynes, that third pi bond is more reactive. But here you want it bulkier, otherwise if you use the borane THF, it'll add twice. Okay, so you'll get to your alkene and then it'll add again before you even have a chance to actually do your tautomerism. The other thing is that here, when you do this, it only adds once because you have some very big bulky groups. So it adds once, you have big bulky groups to prevent it from adding multiple times. So let's talk about what this looks like, and then we'll do our reaction. Okay. So my isoamyl borane. Okay, so amyl is a common older term for a pentyl group. So isoamyl is the same as isopentyl. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And then it's attached to something. That's my isoamyl group. So I have 2 of them. It's secondary. Okay. I forgot my secondary part. I'm sorry. 1, 2, 3, 4 sec. Here's my group. Okay. So isoamyl. This is my secondary. Okay. So when you look at your boron, you're going to have 2 of these groups. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I have 2 sec isoamyl group boron. Okay. So this will basically react with my alkyne in this fashion. And again, we're going to form your four-center transition state, where this begins to break, this begins to form, that begins to break, and this begins to form. Okay? And this is going to be the, okay, so when you're done, that's my transition state, my four-center transition state. So when you're done, I'm going to CH3 here for you. You get this alkene. Okay, and with this alkene, for my second step, just like before, you have your hydrogen peroxide and your sodium hydroxide. Now, just as we've done it with your alkenes, where basically you form your peroxide ion here, it attacks your boron, you get a rearrangement. What you're going to get is an enol. Okay? Your enol undergoes base catalyzed tautomerization. So tautomerism. What you get for your final product is your aldehyde. Okay? So let's go ahead and just summarize this really quick. If I take the terminal alkyne and I add in my dissect isoamyl borane, and then step 2, hydrogen peroxide and sodium hydroxide. My final product will be an aldehyde. Okay? So my water is adding in the anti-Markovnikov orientation. Okay, so what we've seen in terms of the additions for alkenes is pretty much what we're seeing for addition with alkynes. Only differences we see are trying to have some minor modifications to our reagents just to make sure they aren't as reactive. And then there's some additional types of rearrangements going on. Okay, so let's go through, in this case, a base catalyzed tautomerism. So the mechanism for base catalyzed tautomerism looks like this. Tautomerism. Okay. Is you again form your enol rich. This hydroxide can take this proton and that proton. Let's move the electrons over here. Okay, so when you do that, what you get is this anion. And you formed water. So now, my anion takes the proton from the water and you regenerate your hydroxide catalyst. So when we do the reaction with the mercuric sulfate to get the Markovnikov addition of water across my triple bond, you have acid catalyzed tautomerism. When you do your diisocyl boring followed by basically the oxidation with hydrogen peroxide. So when you do that addition of water in the anti-Markovnikov orientation, you're going to be using base catalyzed tautomerism, and you end up generating your aldehyde. Okay. So what other reactions can we do to alkynes? And then we will summarize this at the end. Okay, so we have oxidation of alkynes. Okay, so when you do alkynes, okay, what you can do is you can use potassium permanganate. Remember last time we used potassium permanganate under cold basic conditions, and you formed your diols. When you warmed it up and you started heating it up, they get cleavage. So if I use potassium permanganate in water and it's neutral and cold, okay, then you add OH groups here, and when it rearranges, you actually lose 2 waters and you form the diketone. Okay. What happens if it's more concentrated and you heat it up? So if I take potassium permanganate, alright, basic, and you heat it, okay, you're going to get 2 carboxylates. And then, with our second step, you're just going to add a little bit of acid, and you generate your carboxylic acids. Okay, so oxidation of alkenes we saw previously. You use potassium permanganate with water, a little bit of base, but we had to make sure it was cold. You added OH groups across my alkene. Here, what happens is you do add your hydroxyls across your alkene. You end up losing water because what's going to happen is then you form the diketone. For alkenes, I'm always going to refer back to alkenes because once you know that chemistry, the alkynes just flow right into it. In the alkenes, when you had a warmer potassium permanganate, okay, and you had it in base, all right, what happens is you cleave the bond, okay? In this case, again, we do cleave the bond. But remember, we're in base, so you're going to get the carboxylate, and then we just have to acidify it to get our final product, okay? So let's take a look. So when you have R prime here. Okay. So when you have the potassium permanganate cold, right, and neutral, remember you form your ester, which then leads to the syn addition. Okay, so you're forming a diol, but in this case, I still have a double bond. So then it continues to add okay. So you don't really form this. This is like an intermediate. This one you continue to form, and then that's when you lose two waters. Okay? To get your diketone. Okay? We'll do some examples in just a moment. Okay, so let's talk about more cleavage. When we have our alkyne, we have potassium permanganate, basic conditions, it's warm, okay. Then we get our two carboxylates. That we can then work up to get our carboxylic acid. The other way we can do cleavage is this. If you take your triple bond and you do ozonolysis, and then you basically follow it with water, then you're going to get your carboxylic acids. Okay? So this one you'll get the same thing once I work it up with some dilute acid. Okay? So we have two ways of cleaving our triple bond. One, potassium permanganate. Two, ozonolysis. So let's summarize all of the reactions we know of alkynes and then start doing some examples. Okay? So when we start talking about addition reactions, then if you just take hydrogen and palladium, platinum, or nickel, you just form your alkene. So you're going to need two equivalents. If you do less than that, you'll get a mixture of compounds. Okay, so usually we just do an excess of hydrogen gas. If you want to keep this just to an alkene, then if you use Lindlar's catalyst, okay, remember Lindlar's catalyst was palladium, barium sulfate, quinoline, and methanol. Okay, so it's a poison catalyst. Then we have a cis addition of the hydrogens across my triple bond. So you form a cis alkene. If you want a trans alkene, then you use sodium metal dissolved in ammonia, and then you get your trans alkene. Okay, so these are the reactions we know for addition of hydrogen. Then we talked about addition with your halogens and your hydrohalides. So if I take my alkyne, and I'm going to give you a terminal alkyne, I add in one equivalent of a halogen, so we're talking about chlorine or bromine, you'll just form your alkene. And it'll be a mix of cis and trans. Okay? If you have at least two equivalents of your halogen, then you form your tetrahalide. If I add one equivalent of my hydrohalide, and in this case this could be HCl, HBr, or HI. These are only chlorine or bromine. Okay. Then you would get you would basically get your alkene, okay, a vinyl halide, all right? It adds in the Markovnikov orientation. If I have at least two equivalents, both times it will add in the Markovnikov orientation. Okay? Then we talked about reactions by adding water across my alkyne. So if I have my alkyne and I want to add in the Markovnikov orientation, you're going to have mercuric sulfate, you use sulfuric acid and water, okay, and what you form is you form a methyl ketone, Okay? You add your water in the Markovnikov orientation, and then it tautomerizes. If I want the anti-Markovnikov, then you're going to add di-sec-isoamyl borane, followed by oxidation with hydrogen peroxide and hydroxide. Okay? And what you get is your aldehyde. You add your water in the anti-Markovnikov orientation, and then it is base catalyzed, undergoes base catalyzed tautomerism. Okay? If I take I'll just put R group. I'll leave it as a hydrogen here. If I use potassium permanganate under water, make sure it's neutral, and it's cold, then you form the diketone. Essentially what's happening is that because it's cold, you're going to add in the diol acid across your double bond, and then it rearranges to form the diketone. That's under cold conditions. It doesn't take a lot. You start heating it up to do the following. When you have it under warm conditions, okay, and then you work up with a little bit of acid. Obviously not at the same time, they'll just neutralize, right? So what happens is you cleave it. In this first one, you're going to form the carboxylic acid. The second one, you first form formic acid, but it continues to oxidize. So this carbon, this is carbon. In the previous times, I've just been showing R prime, or my carboxylic acid, but whenever you have your cleavage mechanism and you have formic acid, it continues to oxidize until you get carbon dioxide and water. So I just wanted to show you that, to remind you that's what you get. Another way you can do cleavage, and in this case, I'll use an R prime, okay, is you're going to use ozone, and then you're going to have water. And when you do that, you get your carboxylic acids. Now what would happen, okay, if, as in above, okay, you had subjected this to ozone and water. This is slightly milder than potassium permanganate, so this one just becomes formic acid, or the cleavage is right here. Okay, so like we had the aldehyde situation when we did the alkenes, because it was a milder condition. In this case, because ozonolysis is slightly milder, you don't continue to oxidize up to carbon dioxide and water. Okay, so that summarizes all of the reactions that alkynes can do that we know of. Okay, so now what we'll do is we'll do a few examples. Okay, so let's do a few examples based off of our newfound knowledge of alkyne synthesis. Okay, So if I did ozonolysis followed by water, okay, this is not typical conditions that we use for alkene cleavage, because normally we would use something like dimethyl sulfide here in order to get aldehydes. Okay, can you get carboxylic gases with alkene synthesis? Yes, but typically we don't. We use ozonolysis with dimethyl sulfide. So here we're following it by water to get the carboxylic gases, which means that we're doing an alkyne cleavage, and that would occur between this carbon and that carbon. So let's just carry over the carbon to carbon, and then this has a hydrogen to it. Okay, so again, as we did with alkenes, you can use ozonolysis to look for the structure of your alkyne. In this one, we're doing an anti-Markovnikov addition onto an alkyne, adding water, okay, and we form the aldehyde. So that means that this is where my OH adds, and this is where my H adds, so I have a triple bond right there. So 1, 2, 3, 4, 5, and this is where my triple bond is. Remember, triple bonds are linear, so it may be easier. 1, 2, 3, 4, carbon, triple bond, carbon, and that's my terminal. Now what happens if it were internal? You get a mixture of products, right? So this is my starting material here. In this one, sodium, ammonia, I'm doing actually hydrogenation. I'm adding hydrogen across it, but in this case it's going to give me transorientation. Okay, so that's how you go through and do these examples. Now, let's just do a retrosynthesis. Okay, so when you do your retrosynthesis, okay, that was kind of cute. Let's say you want to make a mesohexane 3,4-diol from acetylene and any materials reagents 4 carbons or less, and then our common reagents are acceptable. Okay, so we're making a mesohexane 3,4-diol. So let's draw this out and find out. So if it's a meso, 1, 2, 3, 4, 5, 6. You have 2 chiral centers here and here, right? 1, 2, 3, 4. Okay, so we're talking about the 3,4-diol. But if it's meso, that means that here's my ethyl group, here's my hydroxyl, it has to have an internal mirror plane. Okay, so this is your meso compound. Okay, so this is what we have to make. Alright, so let's go backwards and start talking about what we know. We're going to start off with acetylene, is one of our starting materials. And let's see, 1, 2, 3, 4, 5, 6. Okay, so our compound that we want to make has 6 carbons. So we're going to be looking for something that has 4 or something that has 2, but we don't want any odd carbon, hopefully. But we'll see what happens. Let's take a look. How do you make a diol? So all the ways that we know how to make diols. Okay, and this is why you want to come up with a list of everything you know in terms of halogenation, radical halogenation of alkanes, all your reactions of alkanes, all your SN2s, all your SN1s, E2s, E1s, all the conditions. Then when we looked at alkenes, all of your reactions of alkenes, how to make alkenes, now all the reactions of alkynes, and how to make alkynes. So that you can just say, oh, listen, I have a diol. Do I know how to make a diol? And the answer is yes. If you have an alkene, you can use, oh my goodness, potassium permanganate, right? And remember, this had to be cold, okay? And we're talking about with a little bit of base. Make sure it's dilute, and you can make a diol, right? If it were concentrated and warm, you would cleave the bond, right? Now, how else can we make a diol? You can make a diol using osmium tetroxide followed by hydrogen peroxide. And you can also make a diol if we made our halohydrin first. So basically, you make your halohydrin, you follow it by base, so you make your epoxide, and then you do an acid cleavage. Okay, and when you make it, this is what you make. Alright, so now, of these, which one are we interested in? But notice, everything has to come from an alkene. So, if I want this to be meso, then it seems more than likely that what I want to do is I want to add in my hydroxyl groups together. Now, I don't have to do this. Okay? There are multiple ways that you can do this. Okay? If I use the epoxide opening, then I have to rotate this to find out what the meso compound looks like. So you say, listen, I don't want to do a cis addition. I want to do, let me just rotate this so that this is in the back. Okay, so that's how I want to do it. Then you would adjust your starting material appropriately. So you can choose. The nice part about retrosynthesis is you have multiple ways to solve the answer, and you can choose what you want to do. Me, I already drew it this way. I'm going to follow with this. But it wouldn't be bad for you guys to pursue looking at it in an alternative fashion to see what else you can do. But there is one commonality that you see when we make a diol, and that is my starting material has to be alkene. So, my starting material has to have an alkene right there. And where you get your choice is that, do you want to do a syn addition to form your diol, or do you want to do a trans addition to form your diol? If I say I want to do a syn addition, then my alkene will look like this. And my syn addition, I'm going to choose osmium tetroxide. Okay, so now I'm going to get my hydroxyl groups that add together in this fashion. That'll come out in the front, pushes my hydrogens in the back. Okay, you could use potassium permanganate. So now that we have this, now we have to tell ourselves, okay, so remember, I can have acetylene and any reagents, organic reagents, 4 carbons or less. And you can see here, we can break this up into 3 sections. I have one here, I have one here, and I have one here. So this is 2 carbons, that's satisfied. I start from acetylene and I know how to get an alkene. So that part will be satisfied. And when I look at my alkene, I'm thinking, I need to figure out how to get a cis alkene. And the way you get a cis alkene, because I'm adding 2 hydrogens, is to use Lindlar's catalyst. I just can't write Lindlar's catalyst because I need to put in my hydrogen. Okay. And what do I start with? It's got to be a triple bond here. And then I have an ethyl group here. And an ethyl group here. Okay. Now, how do I make something like acetylene longer? You use an SN2. So if I use an SN2, that means I have to do it twice. So the first one, C triple bond CH. And this is going to be my second one, because remember, I'm working backwards. I'm going to need 1 sodium amide. Remember, you make this with sodium, ammonia, liquid ammonia, and the Fe3 plus catalyst. Once I remove that, it's ready to react. With a primary halide. Okay, so I get this attached right there. How do I get this from acetylene? You do it again. So some space. So I use 1 equivalent, remove this one. I get a negative charge, so it's going to kind of repel the base anyway. But 1 equivalent, remove this one, form my 1 butine or but1-ine, okay, and then subject it again. Now I have my internal alkyne. So now it's a 1, 2, 3 hex 3-ine. Add in Lindlar's catalyst, so I know I have a syn addition of hydrogen when I do my hydrogenation. And then basically do a syn addition again using osmium tetroxide and hydrogen peroxide to form my meso diol. Okay, so that's your retrosynthesis.